Hello, discrete math fans. Now we've previously talked about inverse functions. Remember that if we have a function that maps from x to y, and if that's a one-to-one correspondence, remember that's a function that's one-to-one and onto, and this is also called a bijection. If that happens, then there is a function f inverse that maps from y to x. It has the property that if f of x is equal to y, then f inverse of y is equal to x. It will undo the process. Inverse functions show up everywhere in mathematics. It's a ubiquitous process to talk about taking an operation and undoing it. We do this all the time. The very first operation you talk about undoing is addition, and when you undo that, you get subtraction. Multiplication and division are inverses. You have more in-depth processes, squares and square roots, powers and roots in general, exponentials and logarithms, trig functions and their inverses. And in calculus, you learn about derivatives and antiderivatives. And then at the end of first semester calculus, you learn this big theorem, the fundamental theorem of calculus, and that tells you that differentiation and integration are inverses of each other. If you ever studied differential equations, you learn about the Laplace transform and its inverse, which is a useful tool for solving differential equations. So the key feature of an inverse function is that it will undo what the original function does. So this property is summed up in this theorem. So this is a theorem about composition of a function with its inverse. So if f maps from x to y is a bijection, which then means it has an inverse, so then f inverse maps from y to x is its inverse, then if you compose these two functions, you get the identity function. So f inverse composed with f, you get the identity function on x. If you go the other way, f composed with f inverse, that's the identity function on y. The book gives a careful proof of this. You might consider reading that. It's not terribly important. It's a little bit technical, not difficult, but it's something you could consider reading. Okay, that's all for now.